just flew in yesterday from New Zealand. I'm very tired and jet lagged, so I apologize in advance for pretty much everything. So I gave this talk like for the first time at a conference last year, and the audience was a bit different, like mostly academics and mostly people with no Rust experience. So I've adapted it a bit, but I think like to make it a bit more fun, like please stop and ask questions and try and make it a bit more interactive than it was the last time I gave this. Does this work? Oh yeah, I have to be really close. Okay. Yeah. I can like pretend to be a rock star. Okay. No? It is. Does that work? Yeah? Yeah? Wow. Okay. So why talk about design patterns at all? The kind of the motivation for me for this talk was that I was kind of bored of giving like introductory, like this is kind of hello world and Rust and 20 minutes and hardly covering anything. And I wanted to give people more of a taste of what programming in Rust is really about without having to teach like a 30-hour lecture course on it. And I thought that communicating some of the design patterns that intermediate advanced Rust users kind of use all the time is hopefully a good way to do that. So yeah, that's what I should have been speaking. Okay, so to those of you who are already Rust programmers, which here I think will be most of you probably, I think that design patterns are a great way about communicating kind of the tribal knowledge that's in the Rust community. So we have I think really great documentation for people wanting to learn Rust for Rust beginners. We also have some really great kind of in-depth kind of documentation, like blog posts about really specific language features, going really deep into the mechanics of this. But this is kind of reference material. It doesn't, if you've got a problem, it probably helps. But like if you want to become a better programmer, once you've already learned the basics, maybe not so much. So this is where I hope that kind of like these design patterns can come in and communicate some more of that kind of stuff. So I started a repository. I'll give you the URL at the end of the talk. That was meant to become like a catalog of design patterns in Rust. And I'm going to go over a few of those today. But there's more online, and I hope that people will help me fill that out even more and make it like a better resource. So I'm going to start with something really simple, which is the constructor idiom, which very basic. We've got you want to construct some data. Here we've got a struct foo, and you want to create a new one. And of course, you've got the struct literal syntax, but it's a little bit boilerplatey, so you can make it a little bit simpler by using a constructor function. And we have this convention that you call that new, and you make that an associative function or static method on the data type foo. You can imagine how you would call this. In this case, it's not really doing much use that's very useful. But in real life, you can initialize private variables. You can do some kind of computation. You can set some defaults that it's boring for the user to do manually. It's a very simple pattern, but it's very useful and one that Rust programmers use all the time. So let's kind of step it up a little bit. A constructor function is fine for like the simple cases, but if you've got slightly more complicated data, there's probably multiple ways to set that up. And we don't have overloading in Rust. We can't have multiple new functions with different arguments, which is a good thing. And if you have new x, new y, new z, it rapidly gets boring. And in worst case, you get a combinatorial explosion of constructor functions. So instead, we have the builder pattern. So again, we're making a foo struct. And this time we have a helper struct called foo builder. And we create a foo builder using this constructor function again, but that's not the interesting bit. The interesting bit is that once we've got our plain boring foo builder, we can call a series of methods on that object to set up what will eventually turn into our foo. And we call the finalize method to turn the foo builder into a foo. And here, this is just a very simple example, right? We've just got methods that look like the fields, and we've initialized them to some values. This is not a great use, to be honest, right? You could do this manually much better. But there's no limit to what you can do. You can do some computation. You can make sure like orthogonal features work together in the correct way, and all kinds of stuff. And the nice thing is that you avoid the combinatorial explosion of having constructor functions. Before I go on, that's kind of like the basics of the talk. If any questions so far? Yeah. You only need one builder, but the builder can have, you know, n methods on it, and you get kind of 2 to the n, or what? I'm too jet lagged to even think about math. So you know what I mean? You get like all the possibilities with only the certain number of functions, rather than having to have like a factorial or whatever it is, number of functions. Sure. The question was, do you end up with a combinatorial explosion of builder objects rather than functions? My short answer was no.
Could we repeat the question? I have a mic for the audience.
Awesome. What I was saying is, it sounds like then you have a combinatorial explosion of methods on the builder class.
No, you have a combinatorial explosion in the combinations of methods that you can call. So rather than, so you can imagine for this, we just have 2 functions, f and g. Whereas if you wanted to have possibilities where you take a default of f and supply a g, you take 2 defaults, you take a default of g and supply the f, and you take real versions of f and g, you need 4 constructors. So you get away with 2 functions rather than 4, and you have 3 or whatever. Yeah, that.
Okay.
Okay?
But it is a linear explosion.
Hey, wait, there's a mic.
That's a hard question. Okay, so the next design pattern is kind of one of my favorites. It's entry. And the motivation here is where you've got a collection. In this example, we're going to use a hash map. And it's pretty common that you want to kind of accumulate a bunch of data into your hash map. Say you're just like counting the number of occurrences of some key. So we're going to iterate over a whole bunch of keys, and if it's in the hash map, we're going to increment the value that's in the hash map. And if it's not, we're going to insert 1, because that's the first time we've called it. Now, this is kind of ugly code, right? It's ugly because it's 5 lines to do a really simple repetitive operation, and it's ugly because it's inefficient. Like, you have to actually look up in the hash map twice for either branch, right? You have to first check whether the key is in there, then you branch on that, and then you like have to look up again to find the place in the hash map for insert, or you find the mutable reference in the hash map. So either way, you're doing 2 lookups. Gross. There used to be an efficient way to do this. Okay, it was called find with or insert with, and this is also kind of gross. Like, at least this was efficient, but it's a pretty ugly function. I'm not going to go through all these arguments, but you know, it doesn't look nice, right? Calm down. We have a much better solution. So it's called the entry pattern. So here you get a single function on the hash map called entry. You provide the key, which is k, and it returns an entry. And an entry is simply an enum, and it tells you, you know, is this hypothetical slot in the hash map, is it occupied or is it vacant? And then, just like any other enum, we can match that. And if it's occupied, we can get the value that's there, and we can add 1 to it. And if it's not, we can insert 1. So this is doing just what we did at the beginning, except this time it's efficient because we're only doing 1 lookup, not 2, right? We only do 1 lookup with the entry. The entry saves a pointer into the hash map, and and then we can just use that pointer again without having to look it up again. So great, that's efficient, except it's still kind of ugly. We've still got this match, we're still doing all this, it's not great. So we can do one better than that, which is there is a method that we implement on the entry called insert. And if there's something there, then it just gives you back a reference to it, a mutable reference to it, and we can add 1. And if there's not something there, then it initializes it with the value that we provide, in this case 0. Again, we add 1, and we end up with what we had before. So now we've got a nice solution, right? This is efficient. We're still only doing 1 lookup, and it's short. It's 1 expression, right? So, this is, I think, just pure win that we've got this this pattern. If you're a C programmer, you're like, well, this is beautiful, but I'm also shaking in fear because what you've given me is you've given me a reference into the hash map, right? Like, what happens if the hash map disappears and you're left with a reference into where the hash map used to be, and then you try and insert there, right? This would be a disaster. Now, luckily, Rust won't let you do this, right? And the way it doesn't let you do this is because of the ownership system. We use some lifetime jiggery-pokery here. So the entry that I showed you before was not quite what the entry really looks like. It's still not quite what the entry looks like, but yeah. So it takes a lifetime parameter. And when you get an entry out of the hash map, there's a little bit of sugar here. What's really going on is this, right? And Rust lets you elide the generic lifetimes, but under the covers, the compiler is tracking them. And you get an explicit lifetime on self, which is the hash map, and that lifetime is propagated into the entry, and then the compiler ensures that the hash map outlives the entry. So if you still have a reference to that entry, the compiler guarantees that the hash map still exists. Okay? And so, like here, this pattern, I said, is one of my favorites because it really demonstrates how in Rust you can kind of have your cake and eat it, right? We've got great performance, we've got good ergonomics, because it's a short, convenient way to do this stuff, and it's safe. Okay? So we've really, it's just pure win, right? Which is, I think, great. So this is another good opportunity to pause and deal with some questions. Anyone's got one?
If you have a question, raise your hand and I'll throw you a mic. Oh, yes, Sarah.
Down here.
Race conditions for first insertion. Question, how does that work?
Can you expand?
Like, two threads trying to insert for the first time into it, if you had equal 1 in both.
So you won't get such a condition because in order to do that, so you're mutating the hash map. So that means you have to have a mutable reference. So what you're positing is you have 2 threads, and each thread has a mutable reference to the same hash map. That's impossible in Rust. The type system forbids you having multiple mutable references to the same thing, whether it's on the same thread or different threads. So that can never happen, and so you never get that race condition. Any other questions? Good night.
I feel like I'm at a baseball game.
Okay, next pattern. So this is a variation on a very common design pattern in C++ called RAII, which is also a really badly named pattern. So the basic RAII idea is you create a value which is stack allocated, and that presumably does some kind of resource allocation. And then when that value goes out of scope, it gets automatically deleted because it's getting pulled off the stack. Its destructor runs, and in that destructor you do some tidying up. Okay, so this is very convenient. And we use this pattern a lot in Rust as well, except in Rust it can be a bit safer, as I'm about to show you. And we can kind of extend using this into using it for all kinds of guarding operations. So the example I want to show you is the Rust mutex. This is a slightly simplified version of how the standard library mutex works. So first of all, you've got the mutex itself guarding some bit of data type T. And then we've got the lock method. So when you want to use the data guarded by the mutex, you have to lock it. And that lock gives you access to the data itself. And when you're done using the data, you unlock the mutex. Usually this is a manual operation, but in Rust we use the RAII pattern to unlock the mutex when you're done with it. And the mutex guard is the RAII object, right? So it has a destructor, that's the drop function. And when the mutex guard is going to go out of scope, the destructor gets called, unlocks the mutex. Going back to the value proposition for Rust, we can look at kind of like the ergonomics bit again here. We can make this a little bit easier to use by using the Deref trait. This is provided for making custom pointer-like objects, and it allows you to have an object that works like a pointer, and when that gets dereferenced, you can programmatically do the specify the behavior that's going to happen there. So in this case, we're going to treat mutex guard a bit like a pointer, and when we dereference that, we get the data that the mutex is guarding. So to see how this works, I mean that was a lot of objects and kind of slightly exotic traits, but the end effect is pretty simple, right? You've got a mutex. Here's an example of that. We've got a mutex that guards a string. We call lock on the mutex, and then we just pretend like we've got the string. Okay? So the mutex guard, when that goes out of scope, it's going to handle the unlocking. And the deref trait allows us to treat the mutex guard a bit like just a plain reference to the string, right? Like you even see when you call this print function that we treat it exactly like a reference to a string. So ergonomics, good. But again, if you're a seasoned C programmer, you're probably shaking in fear here, because what stops you taking this reference to a string, and look at this print method, you have no idea that's come out of a mutex, right? Like, if you're this client and this print function, you don't know what you can and can't do with that, right? So what's to stop you storing this string into some global object? Then the mutex is going to get unlocked, and somewhere down the line, you do some mutation to this reference that you saved because you're a bad person, or more likely you just didn't know. And someone else who's locked the mutex, then they have a race condition. So this is really bad. Again, Rust won't let you do it, and I think it's interesting to see how it does that. And again, it's the lifetimes that save us. So, and again, I lied slightly with my initial code example. So the mutex guard's a little bit more complicated. We've got this lifetime, tick A. And so the mutex guard is saving a pointer into the mutex itself with this lifetime tick A. And so when we lock the mutex, again, we propagate the lifetime from the mutex to the mutex guard. And this means that we can't access the data via the mutex guard after the mutex has disappeared, if that was going to be an issue, okay? And then again, the deref implementation has some lifetimes floating around, and this time we're propagating the lifetime reference from the mutex guard to the reference we're getting to the data. And this means that the reference we get in this implicit deref of the mutex guard cannot outlive the mutex guard. Okay, the type system ensures that. So let's see how that works, like in our example. We've got this lifetime tick A, and I'm making all the lifetimes a bit more explicit than you would usually write here. So this tick A that we see is basically, that's going to last as long as the function foo. And so when we pass that to print, we're going to instantiate this generic lifetime tick B with this lifetime that's foo. And when we do this assignment, the compiler is going to check like this key invariant, which is that when you reference something, the thing you're referencing has to live longer than the reference itself. Okay? And this global thing, this is going to have a lifetime. It's essentially the lifetime of the program. And whatever lifetime tick B is, that can't outlive the lifetime of the program. Or, sorry, you could find versions, but you can't guarantee that for every version of tick B. And so this is going to fail with type checking. Okay? So where this will fail is exactly on that assignment. It's not going to work. And so that's how you prevent kind of the reference into the mutex kind of escaping into the wider world and allowing these race conditions. So, sorry that was a little bit kind of complicated with all the lifetimes. You should be reassured that like 99% of this happens behind the scenes. You don't need to deal with it like when you're doing Rust programming. Most of the time, like if you're writing libraries, you have to think about it. Most users don't. The compiler takes care of it for you. You get your safety, and it's not too bad to work with. Okay, so probably again a good place to stop if someone has some questions. Yeah.
So I always get confused about how the lifetimes flow through code like this. How does you get a lifetime tick A in foo, and it somehow is propagated into print? How is that happening?
Okay, so this is a little bit tricky to explain because you can't write all the lifetimes in the same way that you would like with type parameters, say. But if you imagine this is just like a generic method with type parameters, then when you call it here, you would specify like the type parameter that you're instantiating. Mm-hmm. Likewise, the compiler is specifying here a lifetime parameter, which is instantiating tick B.
But I can't say it explicitly. How does it figure out which one to use, what lifetime to instantiate at print there?
The compiler just infers, so it looks at the variable here.
I see. So it actually
tick B is tick B, and it infers what the lifetime here is.
So it actually throws from right to left in print. It says, S is a tick B string and reference, and so print must have to have lifetime tick B in its parameter, rather than the other way around.
Essentially.
The scope kind of initially inferred from the scope where the variable is declared.
So in this particular case, like it's a little bit more complicated than usual because you've got the implicit deref happening. So this S is a mutex guard value, and then what's happening here is that we implicitly kind of deref that into the value itself, and then reborrow essentially what comes out of the deref. And so there's a borrow here that the compiler knows is going to be, in this case, kind of with scoped by this expression itself. And so it's that lifetime, there's essentially this bit of this expression that's going to get passed into tick B. And you don't have a way to write that, and that's why you can't write it like you would if you wanted to be explicit with type parameters.
So there's no place to put the tick A there that will explicitly show what's going on?
No.
Okay. And you couldn't break it down into two parts where you did something before the print to get that to be a possibility? Could I reborrow explicitly before the print?
You could, yes, and then you'd have a lifetime that basically kind of like started here and ended when it went out of scope,
right.
the curly brace. That would still be fine. The compiler would infer that. You still can't name that.
Okay.
Like, there are proposals that would allow you to do that, and then other hypothetical proposals that would allow you to explicitly put it here. It's maybe useful for kind of debugging your borrow check errors and stuff, which is why we're considering doing that. But right now in Rust, yeah, you just have to trust the compiler to do the inference for you.
Okay, thanks.
I had one note about, there's a trick that I found very helpful in reasoning through questions like this, and that is to keep in mind that the compiler always thinks about each function one at a time. When it's doing lifetime analysis, it does not track anything through one function and follow it through that one and then return to the next one and then go out to its caller. Basically, it analyzes each function separately knowing only the signatures of the other function it calls. And so basically, foo, when it checks foo, it has no idea what print actually does. It only knows its signature, that it takes a reference of a given lifetime and that it does not return it. And all of this, and it has to reason, it has to be able to convince itself that foo is safe, knowing only print's signature. And that sometimes simplifies things a lot because it means that the problem is more local than you might imagine.
Any more? Okay. Then I'll carry on. The last pattern I want to talk about is actually an anti-pattern, which is a software engineering concept. We tell you what you ought to do, and now I want to tell you what you shouldn't do as well. And this is actually my favorite bit because I hate people doing this, and it gives me a chance to rant about it. And the anti-pattern I'm going to talk about is an abuse of the previous trick I just hinted at, the Deref trait, and it's an abuse of that to synthesize something a little bit like the polymorphism that you're used to, or maybe used to, in class-based object-oriented languages. So here's an example of something you might kind of expect to do in Java. This is really obvious. Like, you've got a class foo, you've got a class bar which inherits from foo, and part of that inheritance is it inherits the methods that are part of foo, right? So I've got a variable with type bar, and I can call this method lowercase foo on it, even though that's defined in the class foo. Totally classic class-based inheritance, totally lacking from Rust, which is, again, a good thing. But you know, some people miss it, and occasionally it's a useful pattern, so you try and recreate it. So let's try and do that. The data of this is very simple. We can emulate the data story quite easily in Rust, right? We have some classes foo and bar. Well, let's have some structs foo and bar. We've got a function foo on foo, so let's just implement that function foo on foo. And we can we don't have inheritance, but let's get as close to that as we can by using composition, and we're going to put like a field of type foo inside our struct bar. Okay, so far so good. Like, if we had some fields in foo, they would be inherited into bar. We just need an extra step to get to them. But what can we do about this method? Well, this is where we abuse the Deref trait. And so what we're doing here is we're saying whenever I get something that looks like a bar, then I can implicitly dereference that to a foo. And I call this an abuse because the Deref trait is designed for smart pointers, but clearly there is no smart pointer here, right? Bar is not like a smart pointer to a foo, it is a foo, okay? So we're doing something that's not intended. On the other hand, it works, right? So here we've got a variable of type reference to bar, and we call foo on it, and magically it works. So, you know, it's got that going for it. But you shouldn't do this, okay? So there's a lot of reasons why you shouldn't do it. One, like, it only works like with when you've got the thing by reference. It won't work by values, which you have a lot of the time. Two, it doesn't work with generics. If I have a generic function that expects a foo, then I can't give it a bar. Three, there's no subtyping like you would get in Java or C++. So if I have a function that takes a foo and I pass a bar to it, that won't type check either. Four, it's just surprising, right? Like, this is not how it's intended. So a programmer comes along and they're like, okay, let's find bar, and where's foo? And no, there's no method on bar called foo. What's going on here? And you've surprised somebody who's reading your code, and like, we don't like surprising people. And then there's a whole lot of subtleties, right? Like, you're trying to emulate Java, and you've got pretty close, right? You can call this function foo, but you've missed a lot as well. You don't have, like, class-based privacy. There are no interfaces. If you're trying to get, like, C++, you only have single inheritance. And the behavior itself is slightly different as well. If this were Java, and I looked inside the foo, then it would act like the self inside foo would act like a bar, but in this case it acts like a foo. So you've got subtly different behavior around self as well. So all in all, I think this is a bad thing to do, right? Like you've got a little bit out of it, but you've lost a lot as well. So I would advise against doing this. Okay, I don't actually have a conclusion. I've just shown you a bunch of stuff, and I hope it's interesting. Oh, does anyone have any questions about the last bit before I finish my non-conclusion? Or the whole talk, in fact, given that we're kind of at the end of it. One down here.
Wait a minute, please. Oh.
Would you use the from and into traits for a solution to that problem, a more correct solution?
Sometimes. So they give you a way to kind of convert between different types, and often that's what you want to do, and so it's a good alternative. If you want to kind of temporarily pretend that one type is another, it's maybe not the best way to do that. Like there are traits that do that in some situations, like if you need you want to pretend something's or not pretend, but view something as a reference, then there's like kind of the borrow trait and so forth. So there are some solutions to specific instances. There's no good general kind of alternative yet, but we're working on it. Any more questions? Okay, so yeah, that's pretty much everything. There's no real conclusion here. Just I hope these are useful, and I hope it inspires you to document more patterns. And if you do, then please contribute them to the pattern repository. And if you're interested in what I talked about, everything I talked about today is kind of also in the repo in much more detail. So check it out and help me out with more patterns if you're interested in that kind of thing. And that's all. Thank you.